Welcome to the pre-recording of the second half of lecture 15, scheduled for the beginning of week 6 in our 8-week summer course on computer algorithms. We introduced an iterative algorithm to compute maximum flow. I will start by running a numerical example just to make sure that this pre-recording is self-contained. In the first part, we showed that the algorithm terminates. However, it's a pseudo-polynomial time algorithm because the running time depends on the size of the numbers. We will say more about this on the optimality and give a modification of the Ford-Fulkerson algorithm, which may reduce the number of iterations. Okay, let's look at what the problem is. We have given a directed graph. It is a weighted directed graph. The weights are called capacities. So we have also in the graph a unique source with only outgoing edges and a sink with only incoming edges. So in the example here, you see S is the source, the vertex T is the sink. There are 4 intermediate nodes, A, B, C, D. The numbers associated to each edge are the capacities of the edges, and we want to assign a flow running from source to sink. That flow assigns to every edge a number that doesn't exceed the capacity. Everything that leaves the source has to arrive at the sink, so there is no leak in this network. And we are going to do this in stages, as this is an iterative algorithm. Here is the first step. We find a path from source to sink. So here I looked at the top edges, and the smallest capacity equals 12. So I can push a flow of 12 along these top edges. So the bottom graph shows this initial flow where we are indicating in thick red edges that we have a flow. As you can see, this is one step in the algorithm. We are not done yet. 12 is not maximum. In order to compute the next part, we have to consider the residual graph. The residual graph is shown here. So on all the edges where there is a flow, we allow for the redirection of the flow. So we draw a backward edge where the value, the capacity of that backward edge is the flow that is on that edge. If there is still a positive flow in the original direction, then we subtract. So we allow for the redirection here of 12 in the edge from A to C. There the flow equaled the capacity, and we would have a forward edge from A to C with a flow with a capacity of 0. That's actually a non-existing edge, therefore we do not draw that edge. Now we can look into this residual graph to look for a path from source to sink. you see that because of this backward edge going from C to A, there won't be any possibility to have additional flow from A to C. But there is still possibility to have a flow of 8 in going from C to T, from C to the sink. Okay, so we compute a path which will be called an augmenting path or augmented path from the source to the sink. And you can see that the path is here given with these dashed arrows. And now we see that the maximum value of the flow equals the minimum residual capacity. So we look at the numbers 13, 14, 7, and 8 along that path, and we arrive at the bottleneck value of 7. So we can push a flow of 7 on this graph. So that's the next step. We push a flow of 7. Okay, so the total flow has then increased to 19. So here you see what we have obtained after 2 steps. So we have the first flow of 12 and the additional flow of 7. Okay, you can see that there is still possibility. We have, for example, we have not used one edge, the edge from D to the sink of 4, so we still have additional room for improvement. So in order to compute this systematically, we compute the residual graph. So for the arrows on which there is a flow, we construct the backward arrows in this residual graph, if allowing for the redirection of flow, and we then compute in this residual graph an augmenting path. Here is the augmented path that we compute. So indeed, you can see that we will be utilizing the edge from D to the sink, adding an additional flow of 4. So 4 is the bottleneck, the minimum value between 6, 7, and 4. Okay, so here then we are pushing that flow of 4, and then we obtain the following result. So we have a total flow of 12 plus 7 plus 4 of 23. Are we there yet? Well, it looks like it, but we have to do this systematically, and that happens by constructing the residual graph. So here we have the residual graph by adding the backward arrows, allowing for redirection of the flow. And now the question is, can we still find a path from source to sink, allowing for additional flow? Let's look at this. Well, you can start from the source and go to either A or B, but if you go from source to A, then you can see that A has then only 2 incoming arrows. So you're stuck. If you go from source to B, then you can only go to A. You cannot go to C. Actually, no, you can go to A, but you can also go to D. But in D, you're stuck as well. So there is no more path in the residual graph from the source to the sink. So that's how the algorithm terminates. So this is a brief introduction on example, just to make this lecture, this pre-recording self-contained. And also to invite for you to practice this. So typically we work with source and sink, but we can say the source has label 0 and the source is the node with the largest index. So here we have 6 vertices and with not that many more edges, so this exercise should run faster than my running example. You must show all the steps in solving this exercise. Computation of the residual graph, finding the path, pushing the flow. Okay, question now. We had the upper bound, the big C, on the number of steps. So if you add up all the capacities, then that is an obvious upper bound on the value of the flow. So V of F is the value of the flow. And this capital C was also bounding the number of iterations. And there is a huge gap. So already on the previous example, I should have pointed this out, the 23, the maximum flow, is much less than the bound C. So, and we were done after essentially 3 steps plus a 4th step that didn't go nowhere. So the number of steps, we only pushed flow for 3 times. Okay, so we're going to try to found a lower bound, and also the computation of this lower bound is interesting to see if the flow, if the maximum flow would be rather too little, where in the network do we need to increase our capacity. So we define a cut that separates source from sink as a partition of the vertex set into A and B. A contains the source, B contains the sink. Now, in a flow network, the capacity of the cut is then the sum of the capacities of the edges that going out of A. Okay, here is a first property. The value of the flow, uh, the maximum value here, or actually the value of any flow, we can relate this to the flow across a cut. So we start from the source. The source, by definition, because it is a source, it has no incoming edges. So the flow on that source is actually what comes out. There are no leaks, so in all the inner nodes, what goes in must go out. Or the flow, the outgoing flow minus the incoming flow equals 0. So what does the flow is then computed by, for all the vertices that are in the first set, the out minus the in. It's kind of strange that for inner nodes, so there will be still outgoing out of the set A. So actually, if for an edge it's both, then actually if both of the vertices lie in A, then there will not be a contribution. So that's why we can restrict ourselves to the edges that are going out of A minus what comes into A. So the edges that are kind of in the boundary. So, and we denoted this as the difference in the outgoing with the ingoing for the set A. So this is a property of the value of the flow. Okay, so then remember that we had the bound on the number of iterations in our Ford-Fulkerson, in the not our algorithm, but the Ford-Fulkerson algorithm. So the bound was the sum of all the capacities. That bound is too large. So we're going to find a new bound, and that bound is actually the value of the flow across that cut. So the cut partitions, so everything, and there are no leaks, so everything that comes out of the first set that contains the source must go into the set that contains the sink. So we can rewrite this, and then we have that for any flow, the cut actually is uh, another bound, a new bound, which is typically sharper than the bound that we had from by summing all the capacities of all the edges. Now we only need to consider the capacities on the edges. So the proof is an exercise in notation. So we have related the flow to the outgoing and ingoing flow in that set A. And we can rewrite this as the sum of all the flows on the outgoing edges. And that is bounded by the sum of the capacities. And I see now that in some sense this proof actually defines what this notation C of A and comma B means. You look at all the outgoing edges out of the set that contains the source. The sum of all the capacities of that defines a much better bound. So that's the important consequence of considering the cuts here. Okay, we have that maximum flow equals minimum cut. So we had our running example with a maximum flow of 23. So there is an obvious way to separate source from sink. Just cut the edges that are outgoing from the source. Just cut everything that is incoming. These are cuts as well. Some sense you can call them trivial. But actually the minimum cut here is the most interesting one. I've indicated this in blue. So we are cutting those edges that where the flow equals the capacity. So that indicates that if you want to increase the maximum flow, you have to increase the capacities of those edges in that minimum cut. Okay, here is now a theorem that the algorithm max flow, so this is what we gave the name of our name for the Ford-Fulkerson algorithm, that this algorithm is actually optimal. It returns the maximum flow. Well, how does this happen? Well, recall that from the running example, we stopped when we could find no augmented path in the residual graph. So G sub F is actually the residual graph. If there is no path from source to sink, then we terminate. Well, if that happens, so what the theorem says, then you can find a cut separating source from sink for which the maximum value equals that cut. And that maximum flow equals the minimum capacity of that network. So in some sense, that maximum flow gives you a very sharp upper bound. So if your maximum flow in the example is 23, then you should do at most 23 steps. That's the practical implication of this. Okay, let's try to prove this. So we have the optimum partition. So for all the vertices in that A star, we do have a path from source to sink in the residual graph. Note that the algorithm stops again when there is no path from source to sink. So once we have A star, B star is just a complement. B star contains then the sink, and we have thus a partition. Okay, let's verify that that is a cut. Okay, so by definition, the fact that we defined B star as the complement, we have already a partition. So there is no path in the residual graph from um, any vertex in A star to B star. So consider now this cut. So we have U to V, U prime to V prime is actually the backward arrow. Okay, so what can we say about the flows? So in a forward path, uh, between two vertices across the cut, we have that the maximum capacity is reached. Or the backward, for the backward edge, we would actually not have drawn it because there is no flow there. So we have no flow um, on the backwards anymore. So let's try to verify this, and this will be done by contradiction. So we have to assume that the flow is less than the capacity. If we would have that the flow would be strictly less than the capacity, then we could still extend the flow. We could still add flow to it. But since there was no augmenting path from source to sink anymore in that residual graph, this cannot be. Okay, that's the first statement on the forward edges. On the backward edges, assume that there would have been. So what this actually means that this flow is zero on a backward edge means that you can't redirect any flow. Suppose that you would have had still flow there, then there would have been a path that was that could have come augmented. But again, in this residual graph, that was not possible because the algorithm stopped. Okay, then we have the lemma that said that for any cut, we have that the value of the flow is the outgoing minus the incoming for the set A. Let's apply this now on this set A star. We have that for all the backward arrows, there cannot be any flow. Then actually, when the algorithm terminates and we have that partition, then actually the value of the flow must equal the cut. Okay, that's a very important property that dramatically decreases the running time. You can also say that if you have to wait longer, well, you're going to have a much better result. You're going to have a lot more flow. So in some sense, the pseudo polynomial bound is in that respect not that bad. If we have to wait longer, we have a larger value of our flow. Okay, this shows most importantly that the flow is optimal, so we indeed have a maximum flow. And if we have a maximum value, then actually we can compute that cut in time proportional to the number of edges. Now we can follow the proof of a previous theorem, but also you know that in running the Ford-Fulkerson algorithm, we compute a path from source to sink in the residual graph, and for that we run the breadth first search. So you will find all the nodes that can be reached from the source by, say, by the breadth first search tree, and we have shown before that this can be run in a running time of m plus n, bounded linearly in the sum of the edges plus the sum of the vertices. Now our graphs are connected, so m is at least n minus 1, so we can simplify this bound that m is the upper bound, linear time to compute the value of the cut. And once we have the nodes that are connected to the source in this residual graph, then we can simply compute the complement. And we have thus the partition. Okay, very well. So here are the important results. We have that the value of the flow computed by the Ford-Fulkerson algorithm equals the value of the minimum cut. And therefore, the maximum value of a flow from source to sink is equal to the minimum capacity of a cut that separates the source from the sink. Okay, what can go wrong? Well, we could still have to, would still need to do a potentially very large number of iterations. So these cases are probably pathological, but here is such a case. We follow the topology of our simple example of the previous pre-recording at the beginning of this lecture, simply with other values. Suppose that for the first flow you choose a flow of 1 visiting the vertices u and v, which are connected with a path with capacity 1. So the initial flow has 1. Why would you do that? Well, perhaps because it was just how the algorithm worked. Depth first search, the vertices SUVT, so you choose this path. Now, obviously, the bound is 200, and that's here the bound that you get from the maximum value. So the capital C would simply add up everything, which would be 401. So in some sense, the bound here is the cut when you separate the source from the sink, the source, and separate also the sink. Now, what happens now? You compute the residual graph and you find the augmenting path. The augmenting path actually redirects the flow of 1 from V to U, and you have 1 that's the bottleneck. So the next step in this algorithm is that we are going to add 1. So we have added 1, and then we do it again. So each time when we are stepping, we always have to redirect flow from V to U. Okay, we are going to have 200 steps in our Ford-Fulkerson algorithm, or actually in the basic version of the Ford-Fulkerson algorithm. So 200 augmentations will be needed. And that's kind of not very good. How can we prevent this? Well, you should, in the first place, not have selected. You should not have started that way with constructing or selecting a path that had such a low value. So here is the idea of the scaling max flow algorithm. We will actually, in our residual graph, work with a threshold, a delta, that will disregard all the edges in the residual graph that have a capacity less than that delta. So that's the scaling parameter. We You could say that when I was running the algorithm, so if you run this by hand, you don't want to do too many steps. It pays off to look around a little bit. I did 12, 7, and 4, so to select kind of the paths that will give you the largest flow. This algorithm tries to do this as well. So of all the possible paths in the residual graph that you can take, you will not select the edges that have capacity less than delta. Um, and each step you lower the delta value. So here is the scaling max flow algorithm. It's a little bit more complicated. We compute the sum. So we don't, I mean, actually, we would like to compute the maximum cut. So the next exercise will actually ask to run this example. So you will actually start with the bound 401, the sum of all the capacities of all the edges. And you will actually not find a path that, so we work with a power of 2. Uh, and I think the largest power of 2 is 256. You will not find a path where the edges have 256. So there will be no path. But if you don't find a path, and that can be done very quickly, you will cut it in half, 128, also no path. Then you get to 64. And then you can find your paths, and it will pay off. So the exercise, and I was actually saying how it would go, you start with the value C, summing up all the capacities, 401. The largest power of 2 less than 401 is 256. You can't really get out of the source, so finding no path in this graph is very straightforward. 256 is simply too large. Also 128 is too large, but then 64 will work. So if you have 64 as your threshold, you will not select the uh, edge going from U to V. So you will immediately have 64, and then in your next iteration you will use 32. And then you will much more quickly get to the optimal value of 200. So instead of having to run 200 iterations, it will be a lot less. And the goal of this exercise is for you to calculate how many iterations that you need. 256 was the value of delta where we started. The 2 logarithm of 256 is 8, is 2 to the power 8. So that will be the new upper bound. So um, so we again have to make sure that this algorithm is terminating. We will use the same properties that all the capacities are integer numbers. We will also compute then the bottleneck to be integer numbers. All the flows are integer numbers. So, and we will stop dividing by 2 if the value gets to 1. So that means that we will eventually consider every possibility in the residual graph. And the lemma actually gives a new upper bound. So we consider no more iterations as the 2 logarithm of the uh, cost, the sum of all the capacities. Okay, I'm almost there. So it's important to note that why is this true, this logarithm bound? Well, what we have is that we augment the value of the flow with at least delta, because the delta is what we consider. We have a path where all the capacities were at least delta in the residual graph. So the lemma is just emphasizing this. Um, so at the end, actually, the flow is already very close to the maximum possible value. You could see this a little bit in as the uh, binary expansion of the maximum flow value. We've seen the divide and conquer algorithm to compute uh, the exponents, computing essentially the binary expansion of the exponent. This is similar to this. So the maximum value is actually decomposed. Instead of doing one by one by one, we have large chunks. Okay, um, at the end, so we each time have thus the cut that is also um, growing, and here we relate the cut to the maximum value. So the maximum flow in this network gets therefore always increased by the number is the delta and the number of edges. Okay, the number of augmentations is at most twice the number of edges. So this gives us the upper bound of the 2 logarithm of c. Okay, so we have now a newer bound. So the scaling algorithm finds a maximum flow in m times the 2 logarithm of c, which is an improvement of m times the c value, and it can be implemented to run in at most m square times the 2 logarithm. Okay, I hope that this lecture improved your understanding of the Ford-Fulkerson algorithm. I will end by a comment on iterative algorithms. So in this course we started by graph algorithms, then the greedy algorithms, divide, conquer, dynamic programming. Now we consider iterative algorithms. It's a more complicated algorithm where the graph algorithms are actually one of the subroutines. We will relate this in the next lecture to important applications. So there is a drawback. The algorithms that we consider are more complicated to run, but they apply to a much wider range of problems. Actually, the very first algorithm that we considered in this course was the Gale-Shapley algorithm to compute a stable matching problem. We will see how this relates, so how the Ford-Fulkerson algorithm can actually be applied to find the largest matching in a bipartite graph. It also applies to the sequence alignment problems if we want to find the matching of words. So the bottleneck is that the point of this last comment is that we will start to relate many similar problems, or actually, first of all, very problems that are at first very distinct from each other. So the stable matching problem is actually at first very different from the matching of characters in words. Although when we use matching, it's not. So if you use sequence alignment, it is. Now, what we will do is we will start to relate problems that can be solved by the same type of algorithm, still in polynomial time. So as many problems can be reduced to this max flow problem, they all belong to the family of problems that can be solved in polynomial time, or pseudo-polynomial time if you want to be strict. In the last part of this course, starting in week 7, we will do also these reductions, but then we will consider problems for which no polynomial time algorithm exists. So in some sense, here in this 6th week, running into the end of the course, we are starting to relate problems that can be solved in polynomial time using a more general algorithm than the type of algorithms that we have considered up to now. So I hope that this was interesting, and I stop this recording now.